Welcome everyone. It's a pleasure this morning to introduce our speaker, Jason Wright. It's really appropriate for Jason to give a talk here at the Department of Terrestrial Magnetism because he's actually worked on magnetism, unlike many folks here. He did his undergraduate work at Boston University with Dan Clemens on magnetic fields in the Bach globule B335. He went on to UC Berkeley to his graduate work where he worked on stellar magnetic activity as well as Doppler planet detection. After a one-year postdoc at Berkeley, he went on to Cornell for a couple of years as a research associate. And it's that phase I actually met him for the first time. We were both lecturers at a winter school on exoplanets at National Tsinghua University in Taiwan. And so this fresh-faced young man, even back in 2008, was already a known expert on Doppler planets. So you can imagine why he is an appropriate speaker for today. So after Cornell, he went to Penn State as an assistant professor, and he's now an associate professor as of this summer.
Yes, that's right.
On that.
Thank you very much.
And among other things, he also runs the exoplanets.org database, which is another site along with the Exoplanets Encyclopedia and the NASA database for keeping track of exoplanets. And more importantly, recently he's been involved with this Kepler input catalog object, 84 or something or other, which he has been part of claiming this might be an alien megastructure, which got a huge amount of press lately. Oh boy. Including stories all over the place. Even Al Jazeera wanted to do a story on this. So I don't think we'll touch on that today, but we may get some questions about that one anyway. So,
actually, when I was at UT Austin to give a talk, and Adam Krauss, after introducing me, said I did some SETI research. And he said he's actually got a SETI talk, and I thought I'd take a vote. And he took a vote, and SETI won, and so I had to switch over and talk about SETI instead of my abstract.
And based on your hypothesis about that particular star, actually the Allen Telescope Array spent 2 weeks of time looking for either broadband or narrowband signals and did not find anything as yet. But we'll see what happens. So Jason, take it away.
Okay, thanks.
Please don't give your talk in Chinese.
I won't give my talk in Chinese, even if I could. Well, thanks for having me. It's good to be back. I gave a seminar here, I think 6 or 7 years ago. But it's good to be back and see some familiar faces. I normally can drop this sort of slide for a place that thinks a lot about exoplanets. I'll just show you it's 20 years since 51 Pegasi B. There was just a conference at Open Vaults actually to celebrate this, the discovery by Didier Clos and Michel Mayor. But in parallel, of course, there were discoveries going on by others, including our own Paul Butler. I found this little vintage photo of him at UC Berkeley shortly after he had moved there to do Doppler work. Here is the original iodine cell that was used at Lick Observatory, designed by Paul Butler, who did his master's work at San Francisco State, figuring out the chemistry of what would make the best absorption cell, and that grew out of heritage from Bruce Campbell and Gordon Walker, who we were talking about earlier, who used a hydrogen fluoride cell. And if you know anything about hydrogen fluoride, that's kind of insane. They were doing this chemistry experiment on mountaintops with 100 C hydrogen fluoride, which turns into a horrible corrosive acid on contact with water or body parts. It painlessly burns through skin, and the burns, so you don't even know you've been burned, until it gets down to the bone, and then you have to have amputation. And so that's the sort of stuff they were working with to try and find planets. So fortunately now we have iodine, which is indeed medicinal. And it was, I guess, Robert Howard at Carnegie Institute, Washington, that suggested iodine, I found in an article somewhere. Here's a picture of Paul at San Francisco State in 1988. I included this one just for you guys.
We need a poster of that.
Working on the Doppler code, presumably, and putting that together. And here's the Doppler lab at San Francisco State with lots of diagnostic plots of radial velocities of various stars. And here's that picture of them at UC Berkeley. With jazz posters on the wall. Okay, enough of the detour there. There are two ways to do precise radial velocities these days. One is to use an iodine, an absorption cell of some sort. It's almost always iodine these days, although in the near infrared you can use things like deuterated methane that work pretty well. Peter Plavchuk's pioneered that. And the other way, and so what this does is it lets you turn any old unstable spectrograph into a precise Doppler machine. because the iodine lines imprint on the starlight everything you need to solve for whatever the spectrograph is doing. The other solution is to stabilize, of course, your spectrographs so that nothing ever changes. And I'll be talking about our work to improve the iodine cell method to get well below a meter a second. And we think that we've identified the dominant sources of systematic errors in that method. I'm going to talk about the future of precise radial velocities and what we want to do with these two methods going forward. With the transit method coming to the fore, there, in some quarters, is the philosophy that radial velocities have kind of seen their day, they're not so useful anymore, and I'm going to argue that they're still a critical component of future exoplanet discovery. So let me start by talking about what precise radial velocities told us before the Kepler bonanza, and that Kepler has either helped confirmed or extended, and then I'll talk about how radial velocities can continue that now that we are in the post-Kepler era. So one thing that popped out pretty early, well, not pretty early, I guess it was in 2009 or so, is that hot Jupiters seem to be lonely. When we find multiplanetary systems, they tend to have, and in here multiple planetary systems are the blue dots, they tend to have, the planets tend to have a pretty uniform distribution across period space or semi-major axis space. This is distance from the sun in log units, or from the star, and mass in log units going up with Jupiter here. The hot Jupiters, close into the star, don't have many multiple components, and in fact the hot Jupiters that are known to have additional planets are so few that we sort of know what they all are, Oops, on Andromeda, and so on. And we found a few more, but there's kind of a twist on when they're multiple, what's going on. This was confirmed with Kepler, which found plenty of hot Jupiters, because it's very easy for it to spot them when they transit, showing that when you see the hot Jupiter, you almost never see another planet transiting in that system. And so both from the transits and the radial velocities, we've learned something about how it is that these Jupiter-mass planets can come from where they typically like to form and move in. Whatever causes that to happen is inconsistent with having other planets that you can detect via transit or radial velocity. And we'll get back to that mystery. Another thing to keep in mind is that the transit discoveries are preferentially biased towards very close-in planets. And so if we're talking about giant planets, that means we're talking about migrating planets. They were not born where we find them. So the transit discoveries, and this does not include Kepler in this plot, tend to cluster at very short periods, 3 days or so, just because of that selection effect. Radial velocities, the amplitude of your signal drops only as the square root of the semi-major axis. And so when you're talking about giant planets, what limits your ability to discover them is not necessarily your radial velocity precision. It's usually the duration of your surveys. So having only been doing this for 20 years, we can only get 2 complete orbits for things with 10-year periods or less. And so anything out here is a partial orbit. And that's what's causing this ramp down on the other side of the RV discoveries. What this means is that we find the inner planets with transits. We would expect, if everything was independent and random, that radial velocities can then go to those transiting systems, and we should be able to find Jupiter gas giant planets out beyond a couple AU. Now, we've already seen that hot Jupiters are lonely. When we see a hot Jupiter close in, we almost never see another planet farther out. So the question is that also true for the new rocky planets that Kepler and other transit surveys are discovering? And that's really relevant because it is true transit, the discovery pace from transit now exceeds that from radial velocities by a wide margin. You can see the prehistory of planet discoveries, which we were discussing right before the talk, with the hydrogen fluoride cell and other surveys and the pulsar planets. 51 Pegasi gets discovered, and then the RV discovery pace has been steadily increasing until about here, when much of the radial velocity telescope time and personnel effort went into confirming transit discoveries. And here you can see the influence of Kepler coming out with the low-hanging fruit getting discovered right away. And then as the methods became more refined and people got better at figuring out algorithmically which planets had to be real, we moved into 2015, and the number of transit discoveries goes off the top of the chart. Here we go. There we go. And so these are all multiple planet systems discovered via transit with Kepler and validated on the basis of the fact that if you have multiple transiting planets, most of the false positives you worry about go away. So what happened there was a lot of planet candidates moved into the validated pile and got entered into the databases. And there are another 2,800 Kepler candidates to be validated yet. The bottom line, Kepler found planets much faster than radial velocities can confirm or refute them. And so that'll just keep going up. So that explains why the radial velocities have come down. It's because they're busy trying to get the blue curve to go up. One interesting thing we've learned, one of the mysteries from Kepler, is that there's no clean mass-radius relation for exoplanets. The nice thing about transiting planets is you know their radii, and so if you can detect them with radial velocities, then you can get a bulk density, and now we're talking about geology in principle. So here is the planetary radius on a linear scale, with Jupiter being here, so the Earth is down here. The planetary mass on a log scale, so Jupiter is up here where you'd expect. And there is a rough relationship. It's as you expect, the smaller planets are less massive. But that linear relationship doesn't hold quite so well among the giant planets, which is a little puzzling. So there's been a lot of work to try and explain the diversity of densities among giant planets. The color coding here is the logarithmic stellar insolation, that is the amount of flux the planet receives, the total flux energy from the star. And that does seem to have something to do with pushing things up to the right, so inflating the planet. So in some way, the amount of energy the planets are receiving are keeping them puffy and low density. But that story is a lot more complicated than I made it sound. It's not really clear how that works, whether they've inflated them or prevented them from collapsing, or how deep that energy penetrates into the planet. But the point is that radial velocities are what you need to do this sort of work. If you want to get these error bars, which you can see are often consistent with 0, these error bars go down below the bottom, we don't know the masses of those planets. If we want to know them, then we need to be probing masses around faint stars of Earth masses. And that means getting, in short period orbits, so it's doable. But it means getting below a meter per second in the precision. And so this is where the radial velocity frontier is for doing geology on exoplanets. So that brings me to the future of precise radial velocities. I like to think of it in two ways. There are two things we can do. And the first, I think, is going inside out with radial velocities. What I mean is, there's the planets Kepler misses. There are lots of non-transiting giant planets, presumably at 1 AU and beyond. That's where we start seeing giant planets, typically with radial velocities. So unless close and terrestrial planets are lonely, and we don't think based on the solar system that's going to be true, then there's a lot of work to do surveying the Kepler field with radial velocities and finding the giant planets. And it's no problem that these stars are faint, as long as you have a large telescope, because the signals you're looking for are very large. So this is not a precision issue. This is a patience issue, because they're going to take a long time to go around if they're out at 5 AU. We also want to go inside out from the Earth. Jupiter and Saturn analogs in the solar neighborhood, well, we've got 20 years now, so we can actually think about detecting solar analog, or Saturn analogs around the nearest sun-like stars. The new Jupiter analogs are emerging, and so the Saturn analogs, that's what's next. So to do this, what do we need? We need longer time baselines. We have to keep doing the radial velocities, and we need the time baselines to be extended on large telescopes. We also are going to need an improvement in throughput. Some of the Kepler targets are extremely faint. And I'll explain why that's such a problem with the Hobby-Eberly telescope, which is my primary instrument. But it means that when we think about new instruments, we have to really prioritize instrument throughput, and that when we're putting the instrument on sky, we have to worry about every coupling, every surface, to make sure we're getting all the photons we can, because the good old days where most of the stars you're interested in are in the solar neighborhood, and things of 7th magnitude aren't here. Now we're talking about 15th magnitude, and that's an entirely new problem. So this has begun. We have much of the time baseline we need, and the Jupiter analogs are indeed emerging. Here was the first really good Jupiter analog around a G-star, which I published 6 years ago. Nice circular orbit, nice 10-year period. It orbits a G8 star. It's one Jupiter mass, m sine I, just a beautiful signal. Unfortunately, I think this is a pathological case. Most stars do not do this. This star has an activity cycle, which most stars that we look at have. But in this star's case, and almost no others, the activity cycle seems to be responsible for the radial velocity signal. So this is an old source of paranoia that goes back to the 70s, that activity cycles would cause radial velocity signals that look like Jupiter analogs. And in this case, it bit us. But in most cases, it does not. Fortunately, we can monitor stellar activity cycles and check to see if it's a problem. Andrew Howard published another good Jupiter analog, 12-year period, just a year later. And my student Sharon Wong, who will be giving a talk here tomorrow, discovered a nice super Jupiter, but circular orbit, 8-year period with the Hobby-Eberly telescope. And I'll come back to that system in just a second. This is pretty interesting. And we're even starting to find systems where we think there might be something like a Saturn analog going on as well. So 24040, which has been followed both at SOPHIE and Elodie in France, and at Keck Observatory. My student Katarina Feng published this year, although the Swiss published the solution first. One of the problems in having to wait 20 years is that you never know when the other team's going to pull the trigger. And in this case, they pulled the trigger just like 1 year before us out of 20 or something. And so it's this very slow motion, duel. So they got that last point up there, and then they published, and then we published it. Anyway, in this case, there's clearly a trend in the system. So we have something like a Jupiter analog and maybe something like a souped-up Saturn analog. Of course, it could be a stellar binary in an extremely long orbit as well. We don't see any companion for 24040, but it could be there. So we don't know, but hopefully the curvature will start coming down, and maybe in the next couple decades we can say we have a Jupiter-Saturn analog pair. A couple other long-period planets from Katarina's paper. We're now seeing long-period planets, including pairs of long-period planets. These pairs around an M dwarf. And so you can here see that you've got a system with periods of something like 2 years and 10 years, or 2 years and 8 years around this M dwarf system. Jupiter analogs around M dwarfs are pretty rare, so it's kind of neat that we have a couple in a long-period system now. One of the reasons we tend to follow things for a long time is that there's already a planet in the system. And so here's an example of a system where we had an eccentric planet in a 1-year orbit, and long-term monitoring of that system to find why it was eccentric and also to search for rocky inner planets in that system revealed a long-period outer planet as well. I'm sorry, this is the inner planet here with about a 1-year period, and this is the long-period outer planet, which has just almost completed its orbit. One thing we notice is that when you have giant inner planets that are eccentric, or even hot Jupiters, you often find that there is a companion, but it's very far out. So here we have a very eccentric inner planet with a period of a couple weeks, and then you see an eccentric outer planet. This is becoming a theme. And when you have hot Jupiters, and now the density of the inner planet's radial velocity on the sun is so dense you can't really even see it, you find that there's an eccentric outer planet. And so when you monitor hot Jupiters long enough, they go from being lonely to having friends, but these are some friends. They're very cold friends. They keep their distance. They don't come anywhere near you. So we are finding that the rate of multiplicity among hot Jupiters is sort of coming back up to that with other planets. But when we find them, it seems they tend to be way, way out there. And this is probably telling us something about the formation mechanism of these systems. Yet another one, 2 and I think this is the highest ratio, period ratio of any planetary pair outside the solar system. In fact, it rivals the largest ratios of planets in the solar system. And so one of the methods that seems to generate these hot Jupiters that puts them in close, that has been proposed, is the cosine mechanism, whereby an outer orbiting companion, perhaps stellar, perhaps super Jupiter, exchanges angular momentum with an inner object, and if the time scale for the oscillations of the angular momentum back and forth is short enough, the amplitude is large enough, the inner companion can get a lot of eccentricity and then during periaps experience strong tidal forces, which then decrease the energy of that planet's orbit and shrinks it down, and you can generate a hot Jupiter by that mechanism. That doesn't seem to be important for many hot Jupiters, but there are many cases where there is an obvious culprit for an outer Kozai perturber. And so a lot of the systems that we're monitoring with these long-term programs to see these Jupiter analogs way out there have revealed that at least in a few cases it's pretty clear that we understand that's what's happened. So here's another hot Jupiter, HD 17107, and here's the culprit outer companion object with a 10-year period that seems to maybe be the one that's done it. Which brings us back to Sharon's paper. HD 37605 was the first planet discovered with the Hobby-Eberly telescope. It's a 10-meter telescope in Texas. Penn State's about a 1/5 partner. It was discovered by Bill Cochran, and the inner planet has about a 55-day period, and it's pretty eccentric. So we might be seeing something that's been put in there through some sort of Kozai mechanism, perhaps planet-planet scattering has sent it in. But the question is, where's the culprit? And we have been monitoring this because we wanted to know whether this planet transits. Stephen Kane at San Francisco State University now has a program where he finds long-period planets and checks to see if they transit their star. It's very unlikely they do, but there are something like a good 100 of them known, of these giant planets around bright stars in modest orbits, like 55 days. So statistically, you expect a couple of them do transit, but in order to check, you need to know when to expect it. To do that, you need a very good ephemeris. And so we were following up this system, published from HET data, to get that very good ephemeris so that we could point the most satellite at it and see if this planet transits. And it became an interesting exercise for Sharon to learn how to fit the orbit, properly estimate the uncertainties on the transit time, get more data, watch the uncertainties shrink, and then say, okay, now you can schedule most. I'm sure it's going to happen in this window.
Are the data really as good as indicated by those curves?
So this velocity scale here is in hundreds of meters per second.
Yeah.
The precision on these points for this system, the scatter about the fit is 5 meters a second. So yeah, the points are much larger than the error bars. That's the magic of iodine.
Good.
And we can often do several times better. We used some software that I wrote with Andrew Howard called Vealin, which fits radial velocity curves. Sharon wrote a bootstrapping package that sits on top of it to deliver proper parameter estimates. So Vealin provides the chi-square minimum, and Bootstrap provides a bootstrapped set of posteriors. And what we found most, and this is from the paper, this is the most photometry of the system, and this is the transit window here. And the transit depth would have been down to here if there were a giant planet transiting the star. So we ruled out that there was any planet transiting this star, so this planet doesn't transit. And we ruled it out at something like 100 sigma, 100 times, or we would have seen it at 1/100th the depth that it should have been. And our original title was like, we failed to detect transits. And we just felt like any measurement at 100 sigma is not any kind of failure. It's overkill. And so we struggled with how to describe this null detection. It's not the null detection where you looked and you gave up because maybe it didn't work. It's a sort of null detection that closes the book on the entire question. So we didn't fail to find a transit. We showed it definitively doesn't happen. So we call it a dispositive null detection. It disposes of the question. This is actually a term of art from law. A decision is dispositive if it disposes of the question. You don't have to worry about it anymore. So a dispositive null detection would be something like the Michelson-Morley experiment, looking for the ether. It showed the ether does not exist. A more precise interferometer would not have given any more results. They were many times better than necessary to find it. They did not find it. It does not exist. Do something else now. So that's dispositive null detection. We like the term. We've used it. If you like it, please use it. If someone wants to know what it means, you can cite footnote 1 of Sharon's paper. Okay. So if we're going to, so time baselines we're working on. 2, we need throughput. To do the Kepler fields, HET historically has not been good enough. It is a 10-meter telescope, but it has not acted like it. there is a major focal plane upgrade going on at the Hobby-Eberly telescope to do cosmology. But what we like about it is that it will really improve the image quality at the focus of this spherical aperture 10-meter telescope. And so we'll get much better fiber coupling. The starlight will actually go down the fiber almost a factor of 2 better than it has been in the past. And the effective aperture will grow. We'll get to use more of the pupil, so it will now be a real 10-meter telescope. The other problem that we've had is that the way the Hobby-Eberly telescope gets high-resolution spectra to get these meter-per-second Doppler shifts is it takes this 150 micron fiber on the sky, the light's going in. If this is the output end of the fiber, they then drop a slit on top of it to get higher spectral resolution and throw away all of this light. So that is a further reduction of a few in the throughput of the instrument. The new upgraded high-resolution spectrograph will replace the slit with a fiber slicer and essentially slice pieces out of this image and then stack them on the detector like this. It uses a lot more detector real estate, but it gives you all of the light that normally would have been thrown away. So whereas before we would only get one of these slices, we are now saving the light instead of letting it hit the slit and stacking it and putting it through the spectrograph that way.
Is there a loss in just the manipulation of the fiber and that less?
There's a few surfaces in the fiber slicer. Mm-hmm. I don't know the number, but it's small. Right. And so that's, I think, the only losses. We're also getting a new volume phase holographic cross disperser optimized for the iodine region that's going to give us another 30% or so. So you put this all together and we'll finally have an actual 10-meter telescope and we can go after the Kepler field and start our decades-long surveys of Kepler stars. So that's inside out. The other approach is what I call outside in. We know that there are these solar analog systems with things like Jupiter around them. Do they have interior rocky planets? So we want to find the icy rocky planets orbiting the stars, the outer gas giants. It is now actually within our reach to talk about finding super-Earths / sub-Neptunes. So whether there are things like Neptune that have lost their atmosphere or scaled-up versions of things like Earth is for the geologists to tell us after we discover them. In the so-called habitable zone, just meaning that the equilibrium effective temperature of the planet is consistent with liquid water. So to do this, we're going to need, well, one angle is to extend precise radial velocities to low-mass stars. The reason for that is that the habitable zone of a low-mass star, being much less luminous than the sun, is much closer, and so the Doppler amplitude is much higher for planets in the habitable zone. And low-mass stars have very little optical light, so you need to move to the radial velocity, to the infrared, if you want to pursue that route. If you want to talk about stars like the sun, we'll need much better precision. We'll have to go much better than a meter per second to do that, and so we need to understand why the iodine technique has struggled to get below a meter per second. In fact, the only person that's consistently managed to coerce an iodine cell into performing that is Paul. So far.
I think I'd call that accuracy rather than precision. But
No, we are not accurate to a meter per second. We don't know the absolute velocities of these stars to better than a few hundred meters per second.
okay.
This is a differential measurement.
And it is the precision.
It's a real precision. And then we also need to improve the cadence. The stars themselves don't behave at this level. We are hitting stellar noise floors at meter per second. So we do see the stars' radial velocities changing, but that's because of the motions in the photospheres. We need to be able to understand that and model it out. And if we only observe a star every month, then we don't know what was going on. So we need to be able to hit it frequently enough that we see what the stellar motions are doing so we can understand that and correct for them. So let me talk about the first of these, going to low-mass stars. We have a major effort at Penn State to build the habitable zone planet finder at the Hobby-Eberly telescope. Subrata Mahadevan at Penn State, he was hired the same year I was, is the PI on this funded, this NSF-funded spectrograph. Here's one of our grad students on the project advertising the hashtag, for those of you that are on social media, hashtag HPF. You can follow all the latest. So this is an instrument. It's going to go down to Texas next year, I believe. Here is Suvrith examining the grading, having arrived at Penn State, and here is one of the, a cryostat like the one we're using. This is going to be, okay, so the Hollywood pitch version, if I had to explain this to you in terms of successful movies that have already been made, this is HARPS on a 10 meter in the infrared. And like any good Hollywood pitch, it's not exactly that good in every way. So it's a YZJ spectrograph. So it's what the infrared astronomers might call the near optical. Its resolution is about 50,000, which isn't as high as something like HARPS 100,000, but this is plenty for what we're trying to do. And like HARPS, it's temperature stabilized and it's in a vacuum. So this is not like the iodine technique. There's no absorption cell. This is a stable vacuum spectrograph. Nothing will change, and we will use a laser frequency comb to get the wavelength solution as often as required to measure any instrumental drifts that remain and measure the spectra of M-dwarfs. So the goal is 1 meter a second on late M-dwarfs. So there have been many surveys of M-dwarfs at about half a solar mass or larger. These stars have significant optical light. Keck Observatory has been observing them for a long time, as has the Hobby-Eberly telescope and many other telescopes. M-dwarfs are a very diverse set of stars. All of the M-dwarfs, in terms of their mass and luminosity, span as much parameter space as all the other stars put together. So, well, the very highest, those stars. Late M-dwarfs are like a class unto themselves, and they have not been probed because you have to go to the near infrared to study them because their light is so far to the red. So that's what HPF will be doing.
Jason, can I ask,
please.
Still uses a Fourier argon lamp?
They
Or not?
I'm not up on the latest HARPS hardware. I know they've put laser frequency comb light into HARPS. I don't know if it's part of their daily operational.
So it's one or the other. You're going to go with the laser frequency.
We will go whenever you have a choice, you go to laser frequency comb. Thorium argon lamps have a lot of problems with them. In fact, in the near infrared, a thorium argon lamp is totally the wrong one to use. There are few thorium lines and way too many argon lines, which just bloom and ruin your whole detector. A graduate student at Penn State, Stephen Redmond, showed that the proper hollow cathode lamp to use in the infrared is a uranium neon lamp, because neon is the fill gas, does not have those lines that bloom in the infrared, and uranium has lots and lots of lines to choose from. This is an actual image of a real star. So this is the stellar spectrum. You can see the absorption lines, with a laser frequency comb as a test that was done to see if we could do laser frequency combs with HPF. So this is not an HPF image. It's from a Pathfinder instrument that was built at Penn State to prove that this would work. And so you can see the magic of a laser frequency comb. You put laser frequency comb light into your spectrograph, and you get this perfect picket fence of emission lines. And the precise frequencies of the light in each of those picket fence posts is known to atomic clock accuracy. So you are no longer limited by what you think the wavelength of your emission source is. So you're limited by other problems you have putting highly coherent light down fibers and things like that. So this provides the perfect wavelength scale for the spectrograph. You can check it every night, make sure nothing's changed, and if so, calibrate it. And then you can measure the frequency of the absorption features in the star against that wavelength solution and get your meter per second precision.
What's the inset figure?
The inset figure shows how this was done. There are 3 traces here. These are made by 3 optical fibers, 1 pointed at the star and 2 pointed at the laser frequency comb. And they're spaced with smaller fibers because that's the convenient way to get the spacing to be what you want. So these are an actual image, I think, of the 3 fibers that made this image.
They're circular fibers, not octagonal.
In this test, they were circular fibers. The real Habslam Planet Finder needs to do scrambling, and we have some excellent grad students, Arpita Roy and Sam Halverson, who have worked really hard to figure out how to do that scrambling essentially perfectly. And if anyone is interested in those details, I can tell you all about ball scramblers and this amazing way that they found to do that at very high efficiency. something that's in some sense a sensitive subject, but also something that really needs to get addressed is why the precision at the Hobby-Eberly telescope has historically been so poor. The typical scatter about good fits to planets orbiting stars that at Keck Observatory or with PFS have scatters of something like 1 to 2 meters a second, might have something like 3 to 8 meters a second scatter. Unlike high-res at Keck, HET-HRS is fiber stabilized. So you don't have a slit and the star dancing on the slit causing complications. It's in the basement. It's thermally pretty stable down there. It's not swinging around on a Naismith port at whatever ambient temperature and pressure is. And so my student Sharon Wong has been interrogating each of the components that goes into iodine work to figure out which one is responsible, what's different from what's going on at Keck, despite all of the advantages at the Hobby-Eberly telescope. If we crack this problem, and I think we have, then all of the historical data may be recoverable in the sense that we may be able to go back with improved software and rederive much more precise differential radial velocities from decades of data at both Keck and the Hobby-Eberly telescope. So it would be like suddenly, overnight, having 10 or 20 years of radial velocity data land in your lap without having to go observe it. So the components. We have to model the spectrograph. These are not stable instruments we're talking about. And so every time you observe a star, it was doing something a little different to the light. And the shifts involved are hundreds of meters per second, and you have to model very precisely what happened to get rid of that. Perhaps that's not being done as well at the Hobby-Eberly telescope. We've looked at this very hard. It was our best bet, but what we've found is that it doesn't matter what IP model you use, you always get about the same answer. So one rule of thumb is if you're looking for the highest tent pole, the longest one that's holding the tent highest, and you grab one and you move it up and down, and the ceiling doesn't go anywhere, then it's probably not the tallest one. There's something else limiting you. So that appears not to be the problem, although we're still suspicious that there's improvement. It's hard to tell you've helped if nothing you do matters. We also were concerned that perhaps we don't understand the star. What we're doing is modeling the spectrum. We actually say this is exactly what the detector should have seen if the star had a radial velocity of this amount. And to do that, you need to know what the stellar spectrum looks like. And getting those templates right has always been a problem. This is probably not the problem at the Hobby-Eberly telescope, because we can use the templates we got at Keck at Hobby-Eberly, and nothing changes. So it doesn't matter what we use. On the other hand, at Keck, we actually think this is a major source of systematic errors. And that's something that I will let Sharon Wong talk about tomorrow when she's here, because she's done a huge amount of detective work on this and has some very persuasive evidence that she now understands what's going on. This next one, the poor iodine templates. The iodine cell you have to know perfectly. If you're going to use it as a reference, you better understand it, very well, so better than you understand your star. This used to be, yes, of course, what we do is we take the actual iodine cell that sits in the path of the starlight to a Fourier transform spectrograph, which chemists use to measure very precise wavelengths of transitions in molecules, and they give us a resolution 500,000 spectrum of the iodine cell transmission. And then that's much better than we understand everything else, and so that can't possibly be the problem we figured out. But when you're interrogating everything, you double check. So what we did is we went and we got another Fourier transform spectrograph scan of the cell at the Hobby-Eberly telescope. And it wasn't the same. It was different. So Sharon and a research associate at Penn State, Ming Zhao, went to NIST here in Maryland and got a second Fourier transform spectrum. And it's different. And it's not different in any obvious way that would indicate an obvious error. it's not a DC offset. There aren't wiggles in the spectrum. You have line ratios that appear to have changed. Some lines, like these two lines, for instance, the line depth ratio of these two lines are different in the two spectra. So that feels like the cell has changed underneath you. But there hasn't been any monotonic change in the behavior of the cell because we monitored the cell. And so this suggested one of the FTS spectra were wrong or corrupted in some way. Now, this is not the data in FTS obtains. The Fourier transform spectrograph doesn't obtain a spectrum, it obtains the Fourier amplitudes and phases of the spectrum at positive and negative frequencies. And then you transform it to get this. And so it kind of hurts your brain to try and say, how could this line ratio change, and ask where that would have been in the scan. And after worrying about it a lot, we decided that we wanted a spectrum we understood, something in frequency space, not in the frequency of frequency space. And so we got our own R of 500,000 spectrum of a portion of the iodine cell. So here, R 500,000, and this is a real spectrum, not a Fourier transform spectrum. I think it was a real spectrum. So how did we do that? It turns out that there is a high-resolution Estelle astronomical spectrograph at McDonald Observatory. They literally blew the dust off the instruction manual when we asked to use it, and fired up an ancient computer, which is the only computer that can talk to the controllers, to move the components of this spectrograph. It was designed for work on the sun and interstellar medium lines, stared at on like first magnitude stars. No one uses it anymore because it only gives you 1 angstrom at a time. So setting this ancient machine up, which involved hand cranking various things and going back and forth until you figured out where everything was, gives you this much of the spectrum. And Sharon and Ming then, Sharon led the team that over a week took spectrum after spectrum and stitched together a 30 angstrom region. So this is a real Estelle spectrum. I think this has got to be the highest resolution Estelle working astronomical Estelle spectrograph in the world, at least at optical wavelengths. So this is what the iodine cell looks like at high resolution. These are the absorption features that are being imprinted on every star. But only 30 angstroms. This goes on for 1,000 angstroms. But it helps break a tie. And so Sharon's been using this real spectrum and comparing it to the Fourier transform spectra that we have of various cells to see if we can figure out what's wrong with those. In the end, when you do this, it looks like there is something wrong with the cell. We don't think it's aging. And we think we understand which scans are good and which ones we can ignore. My suspicion is that what we're looking at is that the temperature control in the cell has not been consistent. And that on different nights, the cell is actually at different temperatures. And the reason things seem to be changing from underneath us is because the temperature of the cell keeps changing. That's our best bet at the moment. This is something that when the upgraded Hobby-Eberly telescope gets going, this coming year, we'll be able to interrogate. It has a new temperature controller, and we'll be able to finally put this to rest. So I think this has been the dominant problem at the Hobby-Eberly telescope. But along the way to doing this, Sharon has also found what's going on at Keck Observatory and presumably every observatory doing iodine work.
Did this spectrum match the shell too, as well as that? Or?
This Kitt peak spectrum does not match, of that cell, does not match the one that we took. The Kitt peak spectrum of this cell, which isn't the Hobby-Eberly cell, does not match the one that they took on the Estelle spectrograph.
Okay, did you compare it with the NIST one too, or was that one?
So it took a week to get 30 angstroms of a different cell. If we have to do the Hobby-Eberly cell, we will. But to do all 1,000 angstroms would take a couple months of labor of 2 people. And completely occupying that room at the telescope.
How did you eliminate the cell to take that spectrum?
They just used an ordinary quartz lamp.
Okay.
It was kind of faint, but the duration of the exposure was not the limiting factor in that week. It was changing the cross-disperser angle, which involved hand cranking something with a lot of hysteresis. So if you go too far, you have to go back and try again, and the only way to know where you are is to take exposure. And anyway, you get good at it after a few days. And I will let her talk about this later. But we also, Sharon has also shown that an important source of error is Earth's telluric lines. The Earth absorbs certain colors of light, and that's a problem. And I will let her talk about it tomorrow. I really encourage you to see her talk tomorrow. She won't talk about the iodine stuff, which is why I did. She'll talk about all the other things she's done. And I think she'll convince you that sub-meter a second in the iodine should be routine, and that we can do it now. Okay, so I want to finish by talking about another major effort that I'm involved in, and I'll start with this paper for some context. You probably saw the news that there was a claimed discovery of an Earth-mass planet orbiting Alpha Centauri b. discovered with HARPS in this paper by Xavier Demusque. There's a lot of controversy over whether it exists. That's not the reason I bring it up, so I'm not going to talk about it. The point is, this is what finding Earth-mass planets is going to look like in the future. Whether this planet exists or not, when we do find planets, like this one, this is the sort of analysis that will have to be done. So I'm showing you this paper to scare you. Okay, Alpha Centauri b is in a binary, and so in the upper left you see the radial velocities with time of that star. That's the binary orbit about Alpha Centauri A. You remove the binary orbit, and that orbit is now known extremely well, and you get what's down here in the lower left, which is clusters every year of intense radial velocity monitoring. And these are the Fourier powers at various periods that are present in those data. One thing that you see here is this long-term up and down. And so you say, great, we found a planet, but not so fast. If you monitor the stellar magnetic activity of Alpha Cent b, you see it's got the same up and down. And so this is this problem that some stars appear to have radial velocity changes correlated with the stellar cycle, the magnetic cycle on the star. In this case, the semi-amplitude is something like 3 meters per second. And the one that bit me, it was 12 meters per second. For most stars, it's less than 1 meter per second. It is a mystery why some few stars do this and most do not. At any rate, if you zoom in on one season, you see a nice sinusoidal variation. That is chromospherically active parts of the star coming and going as the star rotates. So as Alpha Centauri b goes around, the magnetically active regions show themselves, you get a little more chromospheric activity, and then less as they go around the back. So that's a rotational signal, and that rotational signal can also be seen in the radial velocities. So by fitting both the long-term stellar cycle and the rotation of the star, Demusque et al. Were able to correct their radial velocities for this effect. When you do that, you get something that is very much, but not quite, white noise. This is the Fourier Power, is a periodogram at various periods and log days there. So here's 1 day. And the red lines are some carefully calibrated false alarm probabilities. And there is at least one peak right here that seems to poke above. You don't expect that if you've done your job right at all of the previous steps. This is the Fourier Power from each of their observing seasons in 2008 through 2011. Why not till 2014? Well, we're unlucky that at the moment Alpha Cent A and B are at conjunction. They're so close that you can't put a fiber on one without getting light from the other. And so we have to wait for the orbit to separate them again to pick it up. And so in the meantime, this is the data set everyone's analyzing and poring over it. The next couple of years, they'll finally separate enough that they'll be able to take measurements again and see if the signal is still there. But if they break their signal up into 4 components, you have amplitude in the various colors and phase with the arrows, black being the sum. And all of the other peaks have random phase in each of the years, indicating that it's noise. But the peak at 3.2 days was consistent in phase, which is why the signal grew over 4 years. And so they used that as evidence that they had claimed that they had detected the planet in each of 4 seasons with phase coherence, and so that it was real. So this is what we're up to. This is what we have to do. Why were we able to do this? We, I say. Why was HARPS able to do this? It's because they had intense monitoring. They had the cadence to pick out things like the rotation of the star and properly correct for it. And they can test hypotheses with that dense data set about what they think the source of the radial velocity variations really are. You need a huge number of measurements to find signals that have amplitudes around your precision. So if we want to do this again, we're going to need a lot of cadence, we'll need a lot of observations. This was a huge chunk of HARPS time. Asking to do this 80 more times with HARPS would be impossible because not enough HARPS time. Because it's a general facility, everybody's using it. So the only way to do this is if you have some sort of a dedicated telescope. We want to repeat this experiment on all the nearby stars, but we can't do it if we have to share. And so our solution was to get our own. Now that's hard. Something like HARPS is extremely expensive, the spectrograph by itself, but then also the telescope. But the thing is, nearby stars are bright. And so the exposure times are actually very short. They're too short. So it doesn't actually have to be a big telescope. Stars vary on timescales of 5 minutes, the 5-minute oscillation of the sun, for instance. The exposure time on a big telescope on Alpha Centauri might be 5 seconds. So you actually have to observe many times over 5 minutes to take that out. So you've wasted your aperture. Plus you're spending most of your time reading out. A small telescope is well matched to the problem. So a smaller telescope doesn't hurt you. We calculated that the appropriate aperture is about 1.5 meters. And that's doable. So this is Project Minerva. It's a collaboration among Harvard CFA, University of Montana, Penn State, and the University of New South Wales in Australia. Here's John Johnson, the Harvard PI, David McCready, the Montana PI. It's Rob Wittenmeyer at Australia. And this is the site at Mount Hopkins at SAO's Observatory where this will go. So we knew we wanted 1.5 meters, and we wanted to know how much money we needed to ask for. So we went and collected quotes and some private anonymous quotes from people who had built custom telescopes. And we said, how much was your telescope? And we made a chart. This is mirror diameter of real telescopes. And on the y-axis is how much it actually cost the people who paid for them to get them up and running in log millions of dollars. So you do not want to climb this ladder any farther than you have to. What you're seeing here is the economies of scale that come from industrial production versus bespoke telescopes up here. So each of those, you start from scratch and you design a new telescope. These are coming off of some sort of assembly line in some sense. So why is there an assembly line for 1 meter diameter telescopes? You got to think the anesthesiologist, that's Hobby, backyard observatory in his, Rocky Mountain retreat, and he wants to do astrophotography from, the study on his computer. So these, they're expensive, but they are amateur telescopes. They're designed to last with little maintenance, and they're designed to have very easy interfaces to use. In particular, one company, Planewave, builds a 0.7 meter telescope. They've just come out with a 1 meter model that they are pitching to astronomers. If you go to AAS meetings, you might find these folks with one of these models on the floor, and they pitched to us that these things were ready for professional use, that they could actually handle a dusty environment for years, and that they had done what was necessary to make them a daily sort of thing, which is not their normal market. It's a dual port, so we can put 2 instruments on this thing. The base cost without the leather seats, $185,000. So where does that put us on our curve? And you'll see that Planewave has done something really neat. 0.7 meters and $187,000 is here. They're building big telescopes at much less than other people have paid for them. Of course, it's too small. We want to be here. But we're not imaging. We just need light buckets. We just need light to go into the spectrograph. So we'll build 4. You build 4 of them, and you're at 1.4 meters, and that's where you need to be. And you've avoided the spike that comes from bespoke instruments, and saved yourself factors, and put this into something where you can actually own the whole thing yourself. So we think there are plenty of small telescopes to find. With Minerva, the Kepler spacecraft has showed us that small planets are very common in the solar neighborhood, around stars in general. Down to 2 Earth radii, the frequency of planets that Kepler has found in short period orbits only increases. This is a plot of the period in log space and the mass of planets that are known via transit in blue, radial velocity in purple. This whole space here is empty because you are limited with single measurement precisions of 1 to 2 meters a second. With Minerva, we'll use iodine and Sharon's new techniques to push that down to more like 0.8 meters per second, and then use the cadence we are afforded by our private telescope to get enough data points to explore this whole region that Kepler has told us is full of planets to find. So we'll be the only instrument that is dedicated to a single science project. We will have 100% of this to do the Alpha Centauri experiment on 80 targets. This is basically everything I just said. We guesstimated based on the Kepler results that we'll have something like 14 new detections, 0.4 plus or minus 0.5 of those planets will transit. So if we're plus 1 sigma lucky, we'll get a transiting planet, rocky planet around a nearby star. These are going to be the brightest, most nearby sun-like stars in the sky. These are not going to be these Kepler stars with anonymous 7-digit phone numbers out in a kiloparsec or something. These are our neighbors. These are the stars we'll be studying for as long as we do astronomy. This exists. This is the initial installation of the first telescope, which Penn State purchased back when the project was headquartered at Pasadena. Phil Muirhead's now a professor at Boston University. Here's the proud papa with his fiber acquisition unit that he designed to have the fiber land on top of the star. Here is first light. Depending on who you ask, it was either the Orion Nebula, the Moon, M51. This fuzzy blob is Saturn, which doesn't sound very impressive until I tell you that it was taken with John Johnson's iPhone. We've already discovered planets. The science we're doing until the spectrograph is done is photometric science, so we can do transiting planets. Here is WASP-12, kind of an easy target, but nonetheless, quick look data reduction with a subpar camera and no flat fielding and so this is not as good as we can do. We reproduce the fit parameters in the literature for this star to 1 sigma. Their sigma, not our sigma. So we're, off the bat with these telescopes, and this is from Pasadena. We've never been able to reproduce this at Pasadena. There's some front that came through. Fortunately, we're not in Pasadena anymore. We're now installed fully at Mount Hopkins. We now have all 4 telescopes. Each of the 4 partners has contributed. Planewave has delivered all of them. We've worked out all the kinks, taught them a lot about how to measure mirror reflectivities and stuff. They've taught us a lot about how these things work. It's been a great partnership. And these things seem to be working really well. These are our Aqualon enclosures. Here is some science from Mount Hopkins. Here is a very shallow planet, a transit of an unpublished planet that's coming out soon. I think it's coming out soon. It's not out already. In 7.5 minute bins, we're getting 1.5 millimagnitudes. That's 1.5 parts per thousand photometry from the ground, which is basically as good as you can do. There are ways to do better in certain circumstances, but given it's just a 1.7 meter telescope, this is great. So we know that we can do this science. Once the spectrograph is fully installed, we'll stop doing transits and we'll start the 80-star survey. I want to finish with a quick plug. All of the plots that you saw in my talk about planet parameters, I generated in my web browser at exoplanets.org. Penn State operates in exoplanets.org. It's a very slick interface written, not by me, I don't do JavaScript, but a guy named Otsi Fakuri, a JavaScript ninja, wrote an amazing data exploration set of tools. Every datum that we have on every exoplanet in the database is clickable, and it will take you to the refereed paper from which we got the data with error bars, asymmetric error bars. So here you can see the references. There are many more fields. This table is sortable, it's clickable. You can export the table as you've generated it, and it has a dynamic searcher at the top so you can do complex Boolean queries on the data, including mathematical functions. Every planet has its own one-up page, or detail page we call it, with every single datum that's been recorded. Not all datum are applicable to all planets, but in this case we have transit parameters, and where available we have some radial velocity profiles and transit profiles. The real gem of the website, though, is the data plotter. In your web browser, you have full control over filters and selections. You can overplot multiple picture filters. You have complete control over both axes, font sizes, logarithmic things. You can do logarithmic bins, linear bins on a log axis if you're crazy. It's got all sorts of advanced features, and I made all of the plots that you saw in my web browser. I did not cheat and go to the back end and make them myself. I did all, you can make them too. And what's neat is that if you like what you've generated, here's a scatter plot showing direct imaging, microlensing, radial velocity, and transiting planets. You can actually save your filter as in your browser and come back to it. So when I make this plot, this one was made 2 years ago, if I go back and I open up this plot, it's got more data. It's the same plot, the same configuration, and I can generate a new one and it'll have more data, and I don't have to recreate it. So that's my pitch for exoplanets.org. We're not, the only problem is we're not fast. We're very careful about when we put in new planets. It works at the speed of undergraduates, so we're not always entirely up to date. But it's careful. All the planets are right, or you can't fault us for thinking they were right. So it's a clean catalog. All the data are peer reviewed, and it's got a great plotter. So that's what's it. So I encourage you to use that for all your exoplanet plotting needs.
How does this compare with the database maintained in France?
The exoplanets.eu database. The exoplanets.eu database does not have these nifty plotting features. These are done dynamically in your browser. So it's not like you type in, this is what I want, and you call to a server, and you wait, and it gives you your plot. You push the slider, and this slides around. So your computer is doing the generation. It's much faster. And the data are much cleaner than exoplanets.eu. We believe everything in. Okay. That's it.
Let's thank Jason. Questions? Scott?
So what was your final aperture of those small telescopes?
0.7.
But they are making 1 meter now, you said?
They are now making 1 meter. If we were starting over again today, we'd be behind the curve if we started over from scratch, but we would buy the 1 meters.
Well, could you talk about KIC whatever?
Sure. Can I talk about that after I talk about this? Because it'll be, okay, I'll save that question.
So I have a question about one of the first things he said. I think you were at the IAU meeting a couple months ago, but
I
Kevin,
was.
maybe not.
I was.
You are, okay. Did you see Kevin Schlapp from the
He doesn't think hot Jupiters are lonely.
No, he did it with a Bayesian analysis.
Yeah, I know.
So what do you think about that?
I think we're answering slightly different questions.
Ah.
But to dig into that, I'd have to do my own Bayesian analysis. There are a small number of statistics involved. It's not a strong effect.
Yeah.
When they have friends, the friends are very far away. And so it depends on when you do your analysis to get different answers. Yes, Kevin and I have talked about it.
I assumed that since you're
It's
about
more complicated than I could squeeze into one slide.
You've developed an incredibly good instrument for radial velocity detection, and you found that this correlates with magnetic field strength
In some stars.
in some stars.
Minority.
Now you're also operating on the integrated light
Yes.
from a point source.
Absolutely.
What if you, or is there any potential interest in using this high resolution radial velocity combined with the magnetic fields that you know exist on the sun? Is this a possible application for the future? Because
You want to do precise RVs on the sun?
yeah,
Yes. Xavier de Musc has a solar telescope that feeds the HARPS spectrogram. And he, in fact, just published a paper showing the precise radial velocities they measure on the sun, and they have contemporaneous imaging of the sun. And so in principle, one should be able to test models for what we call RV jitter, how much the radial velocity changes due to stellar motions, by comparing the ups and downs you see to the features on the surface of the sun. And I don't think anyone's done that yet. I'm looking forward to that. What they have done is they've compared to the integrated bolometric flux of the sun, including the ultraviolet, which isn't actually in your radial velocity measurements. But what they've shown is that when the sun gets, I'm going to get this backwards. When the sun gets dimmer, bolometrically, the radial velocities go up.
but that turns the sun into a star
Yes.
because you're integrating light.
And that's why they did it, although they should have restricted to optical, but it's equivalent. That's right. What they're doing is they're showing if the sun were a star, this is what we could do. And I'm looking forward to when they interrogate the underlying models that went into that. And the models say if you have a spot here doing this, then it will cause this RV variation. And that we can check. We have resolved images of the sun. We shouldn't deprive ourselves of those.
Just a related question that brings to mind. To what extent, with that instrument or previous instrument, are the solar reflex motions due to the planets observed?
So just from the numbers, you should be able to detect Jupiter. And then next will be Saturn or Venus, depending what time scale you look at. It's more complicated than that. What we do is we use an ephemeris for the solar system, and we asked what the velocity of the Earth was in barycentric frame, we subtract that, in a Doppler sense. But Jupiter accelerates the telescope as much as it accelerates the sun. Same with Venus, on a similar frequency. So it's not necessarily a well-posed problem to say, can you detect Venus at very velocities? You need to be careful about exactly what you're saying. So I think the better way to ask is, do you have the precision to see, can you see the combined effect of Venus by phasing things up at the synodic period of Venus? Is there one back there? Okay.
If there are no further questions, let's thank Jason again.
We'll get to study.
We'll have an impromptu session on Keck object afterwards.
Afterwards, okay.
Thanks. Thank you.